Right, so last time we were starting to talk about fluids, and in particular, we talk about density, which is mass over volume. I try to use a capital, kind of bold Roman looking V for volume, because we will also be talking about velocity in this chapter, so to avoid confusing volume and velocity, volume always has a capital bold V. So we talked about density, rho, and the pressure, P, which is the force per unit area. And our atmospheric pressure is 1.013 times 10 to the fifth pascals, where a pascal is a Newton per square meter. So I wanted to start by talking about why that pressure is so big. So, what's the source of this pressure? There's kind of two ways of thinking about it. One way is to just think about that pressure as coming from molecules bouncing around in our space, and they collide with us. And every time a molecule hits us, it bounces off. In order to change its momentum, we need to exert a force on the molecule, and so the molecule exerts a force on us. And just basically statistics, when you take billions and billions and billions of particles, all moving hundreds of meters per second, even though they don't have much mass, it adds up to a significant amount of pressure. The other way of thinking about it is just to imagine that the atmosphere is like a big, ocean of gas, and we're at the bottom of it. So if you imagine taking a square meter and putting it on the floor, and then you imagine counting the mass of, of all of the, this is a really bad drawing, but anyway, the mass of everything above it. So just 1 cubic meter of air has a mass of approximately 1.2 kilograms. That's the density of air, 1.2 kilograms per cubic meter. And then if you stack on top of that, more cubic meters, every time you add a cubic meter on top, you're getting another 1.2 kilograms. And this kind of just keeps going up and up and up. Of course, the density of air gets a little less, so eventually, you've got one that's just 1 kilogram, and then 0.8 kilograms, and 0.6, and eventually the air's so thin that, 1 cubic meter might only be a gram. But at any rate, when you add up the weight of all of that stuff, or the mass of all of the air that's sitting above us, then it winds up adding up to a large amount, roughly 10,000 kilograms. So the same thing happens if we dive into the ocean. As we go into the water and we go deeper and deeper, we have not only the weight of this entire atmosphere on us, but if this is the top surface, if I'm down at a certain depth, then there would additionally be a volume of water that is sitting on top of me, and I would have to add the weight of all of that water to the weight of the atmosphere above in order to determine how much pressure I would feel at that depth. Does anyone in here, has anyone ever been scuba diving? No one's been scuba diving? How about just anybody who likes to swim and can swim really deep? No swimmers? Okay, well, I am like a complete baby when it comes to swimming deep in the water. If I go, when I was a kid, I could just go to the bottom of the pool, no problem. But now, 5 or 6 feet, and my ears are killing me. I mean, like serious pain. So You too, Blair. Yeah, I mean, basically, I'm at the point where if I discovered my keys were at the bottom of the pool, I'd have to pay some kid $5 to swim down there and get the keys because I can't do it. So it doesn't actually take too much depth to create enough pressure to be uncomfortable for me, but there are other people who seem to have no problem with it. Who, aside from Blair, who else has trouble when you swim down in the water with your ears hurting? Raise your hand. Okay. And who doesn't have any trouble at all swimming down with your ears hurting? 2 people. Okay, good for you. Uh, so anyway, let's talk about. Keep messing this up. Let's just talk about how, like, what is the formula that determines. Hold on a second. Just having a little trouble with my application. Okay, so imagine we're in the water and we go some depth d below the surface of the water. Okay, and we want to know what the pressure is at this point. So what we can do is we can imagine that there's some area there, and we want to compute the weight of everything that's sitting above this area. Okay, so there's kind of a column of water. The bottom, has an area A. And in order to get the pressure, I would find the force acting on that area, and we know that pressure is force divided by area. So how do I find the force acting on this area? Well, it's going to be, basically 2 components. So the force, I'm going to call this the force at the bottom. So that's the force not at the bottom of the ocean, but just the bottom of this column of water that I'm imagining, whatever's above the depth that I'm paying attention to. The force acting on that is going to have 2 components. One component is the weight of the water, and the other component is coming from the force of the atmosphere pushing down on the water. So that whole, 101,000 pascals, that's the atmospheric pressure, that's pushing down on the top of the water. And so we have that force, and in addition, there is the weight of some additional water. So I'm just going to call that weight of, just the water. So this gives me forces, but I really want pressure, so I'm going to just divide the whole equation by the area A. And what I get is that the pressure at the bottom equals the pressure at the top plus the weight of the water, which would be mass of the water times G over the area. So if I want to know what the pressure looks like at some depth, I need to know how much water I have at that area. But we know that mass of water is related to density. Remember from the previous page, density is mass over volume. So we can replace the mass with the density times the volume. So we would have density of the water times the volume times G over the area A. But what's the volume of this shape? To get the volume of a shape like this, we just take the area of the base and multiply by the height of the shape. So in this case, the area of the base is called A, but the height of the shape is called D. So my volume would just be area times D, and we can replace that. We get the pressure at the bottom equals the pressure at the top plus rho water area dg over the area. And so then the area just cancels out. That's really good because I don't want the pressure to depend upon the area that I'm imagining. And our final relationship then is that the pressure at the bottom, I'm just going to put V and T here, is equal to the pressure at the top plus the density times G times the depth. And let's see, I think Elise and Ziad, I think you were the ones that said you don't have any trouble with the pressure in your ears when you dive into the water. How deep do you, either one of you, think you can go? Ziad?
Probably like 6 feet, not too much.
About 6 feet? How about you, Elise? Can you go deeper than that?
I don't know what I had to do for lifeguard training, but we had to go pretty deep and like pick up a brick. Maybe it was like 9 feet or something.
Okay. Anyone who can top 9 feet? Okay, so let's calculate what the pressure is like at 9 feet, or I'm just going to round it to 3 meters because that's pretty close. So the pressure at 3 meters in water. So first of all, we need to look up the density of water. So when we do that, you know, there's a lot of places we can look this up. A lot of problems are just going to give us the density, but you know, the PDF textbook on Blackboard has a table of densities of common substances, and you can probably easier to just use Google. But if we would look up the density of water, we're going to find that it is, if it's pure water, it's 1,000 kilograms per cubic meter, and if it's salt water, like in the ocean, it's you know, it depends on which sea or ocean. If you go to the Dead Sea, that's a different story. But generally, a good average is 1,030 kilograms per cubic meter. So it's a little bit more dense in the sea than pure water. And I would guess that the swimming pool is probably closer to the density of salt water because you dissolve all of those chemicals in it to, you know, to kill stuff. So let's use the density of salt water. So we're going to have the pressure at the bottom. The pressure at the top we will generally take to just be 1 atmosphere, plus the density of the salt water, 1,030 times 9.8, and then times the depth D, which is 3. Now we better be careful because this is going to give me pascals, and this is in atmospheres, so we want to convert this to 1.013 times 10 to the 5th pascals. And then we'll see what we get from that other term. That's about 3.02 times 10 to the 4 pascals. And total is 1.32. Times 10 to the 5th pascal. Okay, so so that's that's about 30% greater than the air pressure alone, just by going to the bottom of the swimming pool. So it ramps up pretty quickly. For me, 9 feet is already too deep. It's killing my ears. But there are definitely people who can go way, way deeper than 9 feet. You know, in the South Pacific, people have been diving for pearls and sponges, probably still are, just diving, you know, in and collecting those things from, you know, from the bottom of the ocean near their islands. And they can go to pretty impressive depths. Does anyone have an idea how deep a human can go without, you know, special equipment? Okay, then for extra credit, I want you to find out how deep humans can go and compute the pressure at that depth in pascals and in atmospheres. I'll put this up on Blackboard later today, due tomorrow by the beginning of class. But I think if you do this is just a quick Google search, maybe a couple of searches to find, you know, there's different categories of people diving, but look it up, and I think you'll be quite surprised at how deep people can go, and how strong of a pressure that we can withstand without any kind of special equipment. It's pretty impressive. Now, what if we just wanted to get an idea how deep we have to go in order to you know, in order to hit, say, 2 atmospheres, to double the pressure? Hold on a second. Still having trouble with my whiteboard. Okay, so so the depth at which P equals 2 atmospheres, what is that depth? So that would be saying that P bottom equals 2 atmospheres, and when P top is 1 atmosphere, and we want to know what is the depth. And let's do in salt water again. So we would have P bottom equals P top plus rho times G times D. So that's density times G times the depth. And you know, P bottom minus P top equals rho GD. And so the depth would be P bottom minus P top over rho times G. So that's going to be 2 atmospheres minus 1 atmosphere over rho times G. But remember, I don't want these atmospheres. So your chemistry teacher may love it. I may think it's kind of elegant and simple, but when we start mixing it with other things, we need to make sure we're in the metric system. So 2 atmospheres minus 1 atmosphere is 1 atmosphere, and we can write that as 1.013 times 10 to the 5th pascals, and we divide by 1,030 times 9.8. And the depth is 10.04 meters. So basically what this tells us is that for every 10 meters we go down, we add a whole atmosphere of pressure. That's actually really huge. If you think about it, you know, going to assume some of you have watched a science fiction movie where there's a spaceship and, you know, something, the airlock opens or there's a hole inside the ship and just everything starts flying out of the ship because of the vacuum of space. Raise your hand if you've seen something like that in a movie or something. Okay, so maybe most of you. So what's happening there is that you have this huge pressure, 100,000 pascals inside the, you know, spaceship, and outside there's no pressure. And so ordinarily we don't notice this high pressure because there's high pressure in all directions. But as soon as there's no pressure on the other side of the door or other side of the window, I mean, we're talking 10,000 kilograms for every square meter. That's a lot. So that's a difference of 1 atmosphere. And what this is saying is that if you just go down 10 meters in the ocean, you also are creating that same difference. So that's a huge, huge difference. And as difficult as it is to build a spaceship that can withstand the vacuum of space, you know, in a sense, that's how hard it is to build a vessel that can go just 10 meters down in the water. But of course, we have submarines that go much deeper than that. So they may go 100 meters, and then you're talking about 10 atmospheres of additional pressure outside the sub versus inside. Or maybe they go 1,000 meters, a kilometer. James Cameron, the film director, built himself a special submarine so he could go to the bottom of the ocean, which at which you're really talking like 1,000 atmospheres. It's a huge, huge pressure. So anyway, that's a nice benchmark to remember. For every 10 meters, you're adding about an atmosphere. If we would have used pure water instead of salt water, I think it's 10.34. So in fresh water. Okay. Any questions about that? Okay. Let me. I want to show you how a barometer works, so that you can have a sense of how exactly we measure pressure. So the way a barometer works is it waits for the lag of the whiteboard, and then you have basically a cup of liquid. I mean, it could be any kind of stuff, but there. Let's just suppose it's water. Okay, and then we take a tube, but it's open on one end, and then we kind of plug the tube. We suck all of the air out of the tube, so it becomes evacuated. Let's just say it's a vacuum. So that means that the pressure equals 0. Then we take this tube and we place it into the water. Okay, and when we place it in the water, we then remove this plug. And what's going to happen is the fluid is going to flow up into the tube until it reaches some kind of height that will guarantee that the pressure, due to the weight of the fluid, matches the pressure outside due to the atmosphere. So we have what we could call the pressure, outside, and then inside the tube we would have a pressure we would call P bottom at that depth. And there's some depth D. And the fluid is going to move up in this tube until the pressure P bottom is equal to the pressure outside, which means that the pressure outside would be, using our formula, equal just to the pressure at the top plus rho GD. But for the barometer, because we made a vacuum, the pressure at the top is 0. So then what happens is, as the pressure outside goes up, the depth D goes up. As the pressure outside goes down, the depth D goes down. So there's a direct proportionality between the depth and the pressure. Now, if we wanted to make a barometer with pure water, we've already seen that we would need 10.34 meters of water to create enough weight to add an atmosphere of pressure. So the depth D, we would solve for this. It's going to be pressure outside over rho times G, which is exactly what we had here, the pressure over rho times G. So having a 10-meter tall barometer is somewhat problematic. So there's a couple of problems using a water barometer. Pascal himself made a barometer that used a Bordeaux wine, but French people, that's how they think. That wine also has a problem, and the problem is essentially that for water or wine, alcohol, those kind of things, the boiling point is very strongly correlated with the air pressure above the fluid, above the liquid. So if you have water and you have a vacuum above the water will actually start boiling at room temperature or below room temperature. Has anyone ever, raise your hand if you've seen that demonstration in a chemistry class? Nobody's seen that? I always thought that was kind of a cool demo. My teacher in high school, he took a flask of water, he started boiling it, and then he put the stopper in the flask, and he ran the flask under cold water so that it got cold. When it gets cold, all the steam that was filling the flask condenses and creates a partial vacuum above the water, and then because there's a partial vacuum, the water starts boiling again to try to fill that partial vacuum with water vapor. And so then he would pass around. You could hold it in your hand, and it's like it's a flask of boiling water that's cold to the touch. So anyway, the same thing would happen here if we make a water barometer or a wine barometer, that it would start to boil a little bit until we don't really have zero pressure on top. So that would reduce the accuracy of the barometer. Additionally, if you have a 10-meter tall barometer, you need a really tall ladder to be able to read it. Or you need the barometer to be, the cup of water to be in the basement of the building, and you go up to the 3rd floor to read the barometer, except on, when there's a storm, and then maybe you have to change floors because the level of the barometer goes up or down too much. So instead, we want to use a liquid that is more dense, so it can be a shorter barometer, but also something that is not close to its boiling point already at room temperature. And so a good choice for that is mercury. And so we're going to compute the height of a mercury barometer. So the density of mercury, remember Hg stands for mercury. The density of that is 13,600 kilograms per cubic meter. So that's 13.6 times as dense as water. And so if we try to solve for D, it's going to be the P outside over density times G. That would be 1.013 times 10 to the 5th over 13,600 times 9.8. And the depth or the height of the column of mercury would be 0.76005 meters, or we could say 760 millimeters tall. So this is why when we're talking blood pressure or atmospheric pressure, which is described by a mercury barometer, we would measure it in millimeters of mercury, and the atmospheric pressure would be 760 millimeters of mercury. Of course, in my classroom, for a long time, I had a mercury barometer on the wall. We just had a renovation and it was removed. And now I don't have a classroom, but the mercury never reached 760 millimeters the whole time. Every time I would look at it, which would basically be when I would go over this unit, it would be 745, 750, somewhere in that range. And that's because we are above sea level. So as you go up higher and higher above sea level, there's less atmosphere on top of you, and so the air pressure goes down. So this is sort of at sea level, kind of the average depth of the column of mercury. All right, any questions? Okay, let's try a problem from the textbook. Okay, so this is college physics, number 13.6. And I'm going to just kind of mention that the books are not entirely consistent in what they're asking for. So I'll kind of use this problem to illustrate that. It says a reservoir dam holds an 8 square kilometer lake behind it. Just behind the dam, the lake is 12 meters deep. So basically we have this lake, and then there is a dam on one side. And that distance or depth is 12 meters. What is the water pressure at the base of the dam? So part A says find P at 12 meters. And part B says 3 meters down from the lake's surface. So find the pressure at 3 meters depth. So typically a dam is fresh water, so we would use the density of pure water. And they say, what is the water pressure? So the absolute pressure, what I call the P bottom, this is the absolute pressure. But if we want to know the gauge pressure, which is what they are asking for in this problem when they say find the water pressure. When I'm doing problems on the contest, I'm going to always specify, if I want gauge pressure, I will say gauge pressure. Otherwise, I really want this thing, absolute pressure. But they say, what's the water pressure? They're indicating the pressure from the water alone, but not from the atmosphere. That's the same as the gauge pressure. So the gauge pressure would just be rho times G times D. We don't include the pressure from the atmosphere. So in this case, we're going to have just rho GD, that is 1,000 times 9.8 times 12 meters. And that is 1.18 times 10 to the 5th pascals. Whereas the pressure, the gauge pressure at 3 meters would be 2.94 times 10 to the 4 pascals. Okay? So when you're solving problems, I want to apologize in advance. The book, you know, a lot of times it doesn't say the words gauge pressure, but they're actually computing gauge pressure. And when I'm doing them in class, I am primarily, you know, I'm computing the absolute pressure. What I call the P bottom is the absolute pressure. So on the contest, I will always clearly say if I only want the gauge pressure. All right. So, you know, there's few problems for you to do with this concept, but it's not terribly difficult. It doesn't require too much practice. So I'd like to move on and talk about you know, a little bit of a different principle. So far, when we were talking about the pressure, we are kind of implicitly assuming the fluid is not moving, the water's not moving. And I never said that, but that formula that we were using really is making that assumption. Once the water starts moving, there are, you know, the pressure is going to change. So let's sort of get a sense for how that works. So let's imagine we have a hose, and the hose gets narrower. So it has an area 1 and an area 2. And fluid is coming in with a velocity 1 on one side of the hose. And on the other side, it's going out with a velocity 2. And I'm just going to do a little poll and see which of those two velocities do you think is larger? Okay, the velocity of the fluid coming into the hose or the velocity of the fluid going out of the hose. So go ahead and put what you think. Either the velocity in is larger or the velocity out is larger, or they're the same. Just looking for one more response. Okay, so hold on. Can you see those? So what we're getting is 7 people saying the speed is higher on the side out, and 1 person saying it's higher on the speed in, and 1 person who is logged in but not really here. So someone tell me, if you picked the majority vote, why did you say the velocity is going to be faster on the way out of the, you know, on the narrow end than on the fat end? See,
So like typically, the hose where or something where you have like a small gap and there's like a lot of water coming out of it. All that pressure of the water, I guess, getting against that hole causes the water that leaves that small gap to leave in a very high speed or something, or velocity.
yeah, so in other words, you're saying you know this because whenever you try to spray someone with a hose and they try to run away, what do?
You like use your thumb.
Yeah, you cover the end with your thumb, and when you make the hole smaller, the speed has to get bigger. So this is probably about as universal of a thing as I've ever come across. I mean, virtually everybody I've ever met has some point in their life sprayed someone with a hose. Is there anyone in here who never sprayed someone with a hose? See, everybody has sprayed someone with a hose. And when you do this, you know, they try to get away, you want to make the water go faster or farther, and you cover the end with your thumb. And so the velocity is changing. Now, I don't want to get into yet what's happening with the pressure, but hopefully it's clear. And if you've seen this somewhere else other than, you know, with a hose, maybe, you know, nurses might have seen it with a syringe. If you know, kind of squeeze the plunger on the syringe a little bit, it moves in a small amount, but a whole bunch of fluid has to squirt out. Basically, the reason is if you have, let's say, a cubic centimeter of liquid coming in on one side, you need a cubic centimeter of liquid to come out on the other side. And because the hole's smaller, you know, there's a certain volume coming in. We'll call that just volume 1. And the volume 2 has to be equal because the fluid doesn't really compress. That's really true for liquids, but not as much for gases. But gases will still speed up when they try to go through the narrow opening to allow the same volume in to be equal to the volume out. So the principle here is that the volume in, or what we're calling V1, has to be equal to V2, but we're going to try to make it a little more formal. We're going to call it a delta V1 and a delta V2. So delta V1, though, is still just representing the amount of fluid, you know, new fluid that comes into the tube versus fluid that leaves the tube for delta V2. And if we divide this by delta T on both sides, because these two events have to happen sort of simultaneously, then what we get is called the flow rate. And unfortunately, there's not a really uniform notation for this. Some of the problem books call this J, and the PDF textbook calls it Q. So, you know, this is just two different notations. But let's try to get a sense of what, you know, what's going on here. Why does that lead to larger velocity? So the delta volume in, we have an area 1 times what we could call delta x1. And that's how far the fluid has to move as it goes in. And on the other side, the fluid has to move a distance delta x2 to get out. So the volume delta V1 is the area 1 times delta x1. So think of that as like the area of a base times a height of a cylinder. It's going to be area 1 delta x1 then over delta T. And the volume V2 on the way out is going to be the area A2 times the distance delta x2. And we know what delta x over delta T is, just the velocity. So we have A1 V1 equals A2 V2. So this equation is called the continuity equation, also known as the spray your friends with hoses equation. It says that the flow rate Q, I prefer using Q to J, is equal to A1, or just A times V. Let's just call it A times V. And this continuity equation says that the flow rate is just constant. It doesn't change. And that's true as long as our tube does not spring a leak or something. Okay, so let's do a quick example of how that works. Suppose we have a fire hydrant and then we attach a hose to it. So the fire hydrant has a big pipe coming in, bringing water in. Maybe the diameter of that pipe is 6 inches. And the diameter of the hose, the fire hose on the way out, is only 2 inches. So that's, maybe make it a little bit thicker looking. And suppose that the fluid coming in here is going 1 meter per second. How fast is, if we call this V1, how fast is V2? So we're going to have A1 V1 equals A2 V2. And so velocity 2 is A1 V1 over A2. That's going to be the area of a circle is pi r squared, so pi r1 squared V1 over pi r2 squared, and nothing else on the bottom. So we can see that the pi part of it's just going to cancel out. And the radius 1, if the diameter is 6 inches, we have 3 inches. And it's not necessary for me to convert to metric units because I'm going to have inches on the bottom as well. And then the radius 1 is just 1 inch. So those inches just cancel out. And we get a factor of 9 times the original velocity. So that's going to be 9 meters per second. Now, if we wanted our water to spray faster, all we have to do is put a nozzle on the end of the hose where the diameter of the nozzle is, let's say, 1/2 inch. Okay, if we do that, then instead of a 1 inch radius, we would have a 1/4 inch radius. So with 1/2 inch diameter nozzle, our V2 would be 3 inches squared over 1/4 inch squared. And that's going to be 48 meters per second. And if you want it to go faster than that, you've got to get an even smaller nozzle. Okay, any questions? Okay, so let's take a short break, and when we come back, we'll talk about what effect this phenomenon has on the pressure. Okay, so maybe 5 minutes. Help me remember to keep the recording, or turn the recording back on.